Extend systems typically have a limited range, often restricted to line of sight or within the same electrical panel. These systems rely on power line carrier technology, propagating signals through electrical wiring. The range can be further diminished in outdoor settings by obstructions such as trees or metal structures. With a separation of 150 feet and underground wiring, the reliability of Extend is questionable due to signal attenuation. Alternative systems include radio frequency systems and low-voltage control circuits. Z-Wave and Zigbee are examples of RF systems known for their extended range and enhanced reliability compared to Extend. These systems require a central hub or gateway for wireless communication with devices. While range can vary based on environmental factors and obstacles, RF systems generally cover several hundred feet. Varying low-voltage control circuits offers a dependable and adaptable method for controlling outdoor lights. Low-voltage cables are installed either in conduit or directly underground. They necessitate a separate power supply and control unit but provide a dedicated and interference-resistant connection. Considering the distance and outdoor environment, low-voltage control circuits are highly recommended. They offer a reliable, interference-resistant connection and greater range than wireless options. When installing low-voltage control circuits, firstly, use direct burial-rated low-voltage cables suitable for outdoor applications. Secondly, consider enclosing the low-voltage cables in conduit for increased protection. Thirdly, install a dedicated power supply near the barn for the low-voltage control circuit. Finally, select a control unit compatible with the low-voltage system and the desired control methods, such as manual switches, timers, or remote access capabilities. When selecting low-voltage wire size, consider firstly the ampacity of the wire. The selected wire must be capable of carrying the anticipated current load. Consult the National Electrical Code, specifically Table 310.15. D16 for ampacity ratings of conductors based on insulation type and temperature rating. Secondly, voltage drop should be considered. Excessive voltage drop can cause lights to dim or malfunction. Calculate the voltage drop using the formula voltage drop equals 2 times length times current times resistance per 1000 feet divided by 1000. The voltage drop should ideally be limited to 3% of the supply voltage. Thirdly, the environment the wire is in should be considered. For direct burial applications, use underground feeder, off cable or direct burial rated low voltage cable. If running through conduit, THHN or THWN conductors are suitable. Fourthly, the number of conductors needed should be considered. Determine the number of conductors needed for the control circuit, including the power conductors and any control or signal wires. Lastly, local codes and regulations should be considered. Consult local electrical codes and regulations for any specific requirements regarding low-voltage wiring installations. The ampacity of a conductor refers to its current carrying capacity, or the maximum amount of electrical current it can handle without overheating and potentially damaging the conductor or surrounding insulation. Several factors influence a conductor's ampacity, including firstly, the size of the conductor. Larger conductors generally have higher ampacities because they have more cross-sectional area for current to flow. Secondly, the insulation type of the conductor is important. Different insulation materials have different temperature ratings which affect the amount of heat the conductor can withstand. Common insulation types include THHN, THWN, and XHHW. Thirdly, the ambient temperature impacts ampacity. Higher ambient temperatures reduce a conductor's ability to dissipate heat, thus lowering its ampacity. Ampacity tables typically provide ratings for specific ambient temperatures, such as 30 degrees Celsius or 86 degrees Fahrenheit. Fourthly, the number of conductors in a raceway or cable influences ampacity. When multiple current-carrying conductors are bundled together, they generate more heat, reducing the overall ampacity. Adjustment factors are applied to account for this effect. Fifthly, the installation method affects ampacity. Conductors installed in free air have better heat dissipation than those installed in enclosed conduits for raceways, resulting in higher ampacities. Sixthly, the termination temperature rating of equipment is important. The terminals of electrical equipment, such as breakers and panels, have temperature ratings that must be considered. The conductor's ampacity must be selected so that the conductor temperature does not exceed the equipment's termination temperature rating. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. It is an important consideration in electrical installations because excessive voltage drop can cause lights to dim, motors to run inefficiently, and other equipment to malfunction. Several factors influence voltage drop, including firstly, the length of the conductor. Longer conductors have more resistance, leading to greater voltage drop. Secondly, the current flowing through the conductor is important. Higher current levels result in increased voltage drop. Thirdly, the size of the conductor affects voltage drop. Smaller conductors have higher resistance, which increases voltage drop. Fourthly, the material of the conductor influences voltage drop. Copper conductors have lower resistance than aluminum conductors, resulting in less voltage drop. The formula for calculating voltage drop is voltage drop equals 2 times length times current times resistance per 1,000 feet divided by 1,000. Where voltage drop is the voltage drop in volts, length is the one-way length of the conductor in feet, current is the current flowing through the conductor in amps, and resistance per 1,000 feet is the resistance of the conductor per 1,000 feet, which can be found in ampacity tables. The National Electrical Code, NEC, recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Excessive voltage drop can lead to various problems, including firstly, dimming lights. Voltage drop reduces the voltage available to lighting fixtures, causing them to appear dimmer. Secondly, inefficient motor operation. Motors require a certain voltage level to operate efficiently. Voltage drop can reduce motor torque and speed, leading to overheating and premature failure. Thirdly, equipment malfunction. Electronic equipment is sensitive to voltage variations. Excessive voltage drop can cause equipment to malfunction or fail to operate properly. Fourthly, increased energy consumption. Voltage drop reduces the efficiency of electrical systems, leading to increased energy consumption and higher utility bills. To minimize voltage drop, firstly, use appropriately sized conductors. Select conductors with sufficient ampacity and low resistance to minimize voltage drop. Secondly, shorten conductor lengths. Reduce the length of conductors as much as possible to minimize voltage drop. Thirdly, use copper conductors. Copper conductors have lower resistance than aluminum conductors, resulting in less voltage drop. Fourthly, increase the voltage level. Increasing the voltage level reduces the current required to deliver the same amount of power, thus reducing voltage drop. Fifthly, use separate circuits. Distribute loads across multiple circuits to reduce the current flowing through each conductor, thus minimizing voltage drop. Underground feeder off cable is a type of electrical cable specifically designed for direct burial in the ground. It is commonly used for underground wiring applications, such as supplying power to detached garages, sheds, or outdoor lighting fixtures. UF cable consists of insulated conductors embedded in a solid plastic sheathing typically made of polyvinyl chloride, PVC. The sheathing provides protection against moisture, chemicals, and physical damage, making it suitable for direct burial without the need for additional conduit. UF cable is available in various sizes and conductor configurations, including 2-conductor with ground, 3-conductor with ground, and multi-conductor options. The conductors are typically made of copper or aluminum and are insulated with moisture-resistant materials. UF cable is marked with the letters UF to indicate that it is suitable for underground use. It is also marked with the wire size, number of conductors, and voltage rating. UF cable must be installed in accordance with the National Electrical Code and local electrical codes. It should be buried at the proper depth to protect it from damage and should be properly terminated at both ends. Key features of UF cable are firstly, direct burial capability. UF cable is designed for direct burial in the ground without the need for conduit. Secondly, moisture resistance. The cable is constructed with moisture-resistant materials to prevent water from entering and damaging the conductors. Thirdly, chemical resistance. The sheathing is resistant to chemicals commonly found in soil, protecting the conductors from corrosion. Fourthly, physical protection. The solid plastic sheathing provides protection against physical damage from rocks, roots, and other objects in the soil. Fifthly, wide range of sizes and configurations. The earth cable is available in various sizes and conductor configurations to meet the needs of different applications. Direct burial rated low voltage cable is specifically designed for underground installations without requiring conduit. It is used for landscape lighting, sprinkler systems, and other low voltage outdoor applications. Key features include firstly, direct burial capability. The cable can be directly buried in the ground without the need for conduit. Secondly, UV resistance. The cable is designed to withstand prolonged exposure to sunlight without deteriorating. Thirdly, moisture resistance. A cable is constructed with moisture-resistant materials to prevent water from entering and damaging the conductors. Fourthly, durability. The cable is designed to withstand physical damage from rocks, roots, and other objects in the soil. Fifthly, low voltage rating. The cable is designed for use in low voltage systems, typically 30 volts or less. THHN and THWN are types of single conductor building wire commonly used for electrical wiring in residential, commercial, and industrial buildings. THHN stands for thermoplastic high heat resistant nylon, while THWN stands for thermoplastic heat and water resistant nylon. Both THHN and THWN wires are insulated with a tough, abrasion-resistant nylon jacket over a layer of thermoplastic insulation. The nylon jacket provides added protection against physical damage during installation and use. THHN and THWN wires are suitable for use in dry and damp locations, but THWN wire is also suitable for use in wet locations. THHN and THWN wires are available in a wide range of sizes and colors, making them suitable for a variety of electrical wiring applications. THHN and THWN wires must be installed in accordance with the National Electrical Code and local electrical codes. They should be properly supported and protected from physical damage. Key features of THHN and THWN wires are firstly thermoplastic insulation. The wires are insulated with a tough, abrasion-resistant thermoplastic material. Secondly, nylon jacket. The nylon jacket provides added protection against physical damage. Thirdly, heat resistance. THHN wire is heat resistant up to 90 degrees Celsius in dry locations. Fourthly, water resistance. THWN wire is water resistant and suitable for use in wet locations. Fifthly, wide range of sizes and colors. The wires are available in a wide range of sizes and colors to meet the needs of different applications. Conduit is a tube or channel designed to protect electrical wiring from physical damage and environmental factors. It is commonly used in residential, commercial, and industrial buildings to enclose and route electrical conductors. Conduit is available in a variety of materials, including metal, plastic, and fiberglass. Metal conduit is typically made of steel or aluminum and provides excellent protection against physical damage. Plastic conduit is typically made of polyvinyl chloride, PVC, or high-density polyethylene, HDPE, and is lightweight and corrosion resistant. Fiberglass conduit is strong, lightweight, and non-conductive, making it suitable for use in harsh environments. Conduit is available in a variety of sizes and types, including rigid metal conduit (RMC), intermediate metal conduit (IMC), electrical metallic tubing, and flexible metal conduit (FMC), and rigid polyvinyl chloride conduit (PVC). The choice of conduit depends on the specific application and the level of protection required. Conduit must be installed in accordance with the National Electrical Code and local electrical codes. It should be properly supported and secured to prevent movement and damage. Key benefits of using conduit are firstly, physical protection. Conduit protects electrical wiring from physical damage such as impacts, abrasion, and crushing. Secondly, environmental protection. Conduit protects electrical wiring from environmental factors such as moisture, chemicals, and corrosion. Thirdly, safety. Conduit provides a safe enclosure for electrical wiring, reducing the risk of electrical shock and fire. Fourthly, organization. Conduit helps to organize and route electrical wiring, making it easier to install and maintain. Fifthly, code compliance. The use of conduit is often required by the National Electrical Code and local electrical codes. Electrical metallic tubing (EMT) is a type of thin-walled steel conduit commonly used for protecting electrical wiring in buildings. It is also known as thin-wall conduit. EMT is lightweight, easy to bend and cut, and can be installed quickly and easily. EMT is typically joined together using compression fittings or set screw fittings. EMT is not suitable for use in hazardous locations or where exposed to severe physical damage. EMT must be installed in accordance with the National Electrical Code and local electrical codes. It should be properly supported and secured to prevent movement and damage. Key features of EMT are firstly thin-walled steel construction. EMT is made of thin-walled steel, making it lightweight and easy to work with. Secondly, ease of installation. EMT is easy to bend, cut, and install, reducing labor costs. Thirdly, protection of wiring. EMT provides protection against physical damage to electrical wiring. Fourthly, non-threaded connections. EMT is typically joined together using compression fittings or set screw fittings, which do not require threading. Fifthly, cost-effectiveness. EMT is a cost-effective solution for protecting electrical wiring in many applications. Rigid polyvinyl chloride conduit (PVC) is a type of non-metallic conduit commonly used for protecting electrical wiring in underground, corrosive, and wet locations. PVC conduit is lightweight, non-conductive, and resistant to corrosion, making it suitable for a wide range of applications. PVC conduit is typically joined together using solvent cement or threaded fittings. PVC conduit is available in a variety of sizes and schedules, with Schedule 40 being the most common. PVC conduit must be installed in accordance with the National Electrical Code and local electrical codes. It should be properly supported and secured to prevent movement and damage. Key features of PVC conduit are firstly, non-metallic construction. PVC conduit is made of non-metallic material, making it non-conductive and corrosion-resistant. Secondly, lightweight. PVC conduit is lightweight, making it easy to handle and install. Thirdly, corrosion resistance. PVC conduit is resistant to corrosion from moisture, chemicals, and other environmental factors. Fourthly, ease of installation. PVC conduit is easy to cut, join, and install, reducing labor costs. Fifthly, wide range of applications. PVC conduit is suitable for use in a wide range of applications, including underground, corrosive, and wet locations. A power supply is an electrical device that converts one form of electrical power to another. Power supplies are used to provide the proper voltage and current to operate electronic devices and equipment. Power supplies can be classified as either AC to DC power supplies or DC to DC power supplies. AC to DC power supplies convert alternating current AC from a wall outlet to direct current DC, which is used by most electronic devices. DC to DC power supplies convert one DC voltage to another DC voltage. Power supplies are available in a variety of sizes, shapes, and power ratings to meet the needs of different applications. Key features of power supplies are firstly, voltage conversion. Power supplies convert voltage from one level to another. Secondly, current regulation. Power supplies regulate the current to prevent damage to electronic devices. Thirdly, filtering. Power supplies filter out noise and interference from the input power. Fourthly, protection. Power supplies provide protection against overvoltage, overcurrent, and short circuits. Fifthly, efficiency. Power supplies are designed to be energy efficient, minimizing wasted power. Control units compatible with low voltage systems come in various forms, offering different functionalities to manage and automate lighting or other electrical devices. Several types of control units are available, including firstly, manual switches. Simple on-off switches that allow users to manually control the lights. Secondly, timers. control units with built-in timers that can be programmed to turn lights on and off at specific times. Thirdly, photocells. Light-sensitive sensors that automatically turn lights on at dusk and off at dawn. Fourthly, remote controls. Wireless remote controls that allow users to control lights from a distance. Fifthly, smart home integration. Control units that can be integrated with smart home systems, allowing users to control lights using smartphones, tablets, or voice commands. Sixthly, dimmers. Control units that allow users to adjust the brightness of lights. Seventhly, motion sensors. Sensors that detect motion and automatically turn lights on when someone enters the area. When selecting a control unit, consider factors such as compatibility with the low-voltage system, desired control options, ease of use, and reliability. The National Electrical Code (NEC) provides comprehensive standards and guidelines for electrical installations to ensure safety and proper functioning. Several articles within the NEC are particularly relevant to the installation of low-voltage lighting and control circuits. Article 411 covers low-voltage lighting systems, addressing requirements for voltage limitations, wiring methods, and overcurrent protection. It specifies that low-voltage lighting systems must operate at 30 volts or less and must be supplied by a transformer or power supply that complies with specific safety standards. Article 725 pertains to Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. Low-voltage control circuits often fall under Class 2 or Class 3 classifications, which have specific requirements for power limitations, wiring methods, and overcurrent protection. Article 300 addresses general wiring methods and materials, providing requirements for the installation of wiring in various environments. It includes guidelines for the use of conduit, cable types, and wiring support. Article 310 covers conductors for general wiring, including ampacity ratings, insulation types, and installation requirements. It provides guidance on selecting the appropriate conductor size and type for low-voltage lighting and control circuits based on the current carrying capacity and environmental conditions. Article 314 addresses outlet boxes, device boxes, and pull boxes, providing requirements for the installation of boxes used to terminate or splice conductors. It includes guidelines for box fill calculations and the use of appropriate box types for different wiring methods. When installing low-voltage lighting and control circuits, it is essential to consult the latest edition of the National Electrical Code and local electrical codes to ensure compliance with all applicable requirements. Improper installation can result in electrical hazards, equipment malfunction, and code violations.